and curvature. Okay. So arc lengths. So recall, okay, from 2 dimensions, okay, arc length is a to b of the square root of 1 plus f prime of x squared. That's how we found arc length in 2 dimensions. Okay. For 2 dims. Okay, this was the arc length. So we had an arc, and we want to find the length of it. Well, we integrate the distances of the derivatives. Okay, so we use this function here. Okay, this integral to get the arc length in 2 dimensions. The other way to write this is a to b of okay, d dx dt. Let's plug in a dummy variable, dx dt. We want to parameterize this squared plus dy dt. If we put it into parametric form, dt, this is dx. This is with respect to x. This is with respect to a third variable, t. Okay, saying that, you know, x is a function of t and y is a function of t. Okay, so where x is equal to f of t and y is equal to g of t. Okay, a function of t. Okay. Okay, so yeah. In 3 dimensions, we now have an x, y, and z. Okay, we have an x, y, and z. And so we need to just add another dimension here. Okay. So L is equal to the integral a to b of dx dt squared plus dy dt squared plus dz dt. Okay. Okay. Okay, we can rewrite this as f prime of t squared plus g prime of t squared plus h prime of t. We'll let z equal h of t. Okay, plus h prime of t squared dt. Okay, where f is x is f of t, y is g of t, and z is h of t. Okay. Well, if we think of this in terms of, say, you know, r of t, right? R of t, in terms of x, y, and z, okay, we'll say this is f of t, g of t, and h of t, then r prime of t is equal to f prime of t, g prime of t, and h prime of t. Just take the derivative of each of the components. And so what this thing really becomes is this really becomes the integral a to b of, if I dot this with itself and then take the square root, that's really the magnitude. Okay, so this would be the square root, okay, of r prime of t dotted with r prime of t, okay, which is really the magnitude of this thing. Okay, we're taking the first component squared plus the second component squared plus the third component squared. Okay, so this is equal to, okay, a to b of the magnitude of r prime of t dt, and that's L. Okay, let's do an example here. Example 1. Find the length of the arc find the length of the arc of the helix okay, r of t is equal to cosine ti plus sine tj plus tk from the point (1, 0, 0) to 1, 0, 2 pi. Okay, so we have a helix, okay, from 1, 0, 0, okay, 1, 0, 0 to 1, 0, 2 pi. So that's just one rotation, right? One rotation around. Okay, so we went up 2 pi in the z direction. Okay. So say we're starting here and we're ending here. Okay. Maybe we should have started here and ended here, but you get the idea. Okay, it is a helix. Okay, and the distance that we're going up is 2 pi, because that's in the z direction, right? Okay. We're starting at 1, 0, 0, and we're ending at 1, 0, 2 pi. Okay, so we want to know what's the length of that arc. Okay, so well, what I'd like to do is I'd like to find out, well, what's the derivative of this thing? What's r prime of t? Right, and then take this component by component. Okay, so well, what is t in this case? What is let's just see what is t going from? Well, t is really my z component, right? My t times k is z. That's my z component. Okay, well, that means that t goes from 0 to 2 pi, right? 0 to 2 pi, that's what t is. Oh, okay. That's good. Okay. Okay, so I want to know also what's r prime of t in this case. Well, what's the derivative of cosine, negative sine, I? What's the derivative of sine? It's, okay, negative cos, or sorry, is cosine, not negative. Cosine t, okay, this is getting annoying. There we go. Okay, plus k, right? 1k plus 1k. Okay, so that's r prime there. So now what do? I set L to equal the integral from 0 to 2 pi of the square root of the first component squared, sine, negative sine, t squared. And some of you might already see that this thing's going to turn out really nice. Okay, plus cosine t squared plus 1 squared dt. Okay. So this becomes sine squared t plus cosine squared t, and that becomes 1, plus 1 squared, which is 1. So this becomes 2. This is just radical 2. Integral from 0 to 2 pi t, or dt, I should say. This is going to be radical 2 t, evaluated from 0 to 2 pi. So this is 2 radical 2 pi, or we'll put the 2 pi in front. This is 2 pi radical 2 minus 2 pi times 0, or sorry, radical 2 times 0, which goes to 0. So this just becomes 2 pi radical 2. That's the arc length there. Okay. Okay, let's say that S of t is my arc length function. Okay. Let S of t be an arc length function. Okay, then S of t is equal to a to t, okay, of r. We need another variable other than t here. I think fundamental theorem of calculus. Okay, r prime of u du. Okay, so we kind of have a dummy variable there, so that when we evaluate this thing and integrate, we get a function of t. Okay, we get a function of t. Okay, and so what we can say here is we can say that ds dt. Okay, so we took the derivative of this with respect to s. Is it with respect to t? No, it's with respect to t. Okay, take the derivative with respect to t of s of t is equal to the derivative with respect to t of a to t times r prime u, okay, du. Then, according to the fundamental theorem of calculus, this thing, the derivative of s of t, which is s prime of t, would just be equal to what's inside here, okay, evaluated at t. Okay, so this is going to be r prime of t. Okay, it's just the magnitude of r prime of t. That's the derivative of the arc length function. Okay. Okay, let's look at this example here, number 2. Let's reparametrize the helix r of t is equal to cosine t I plus sine t j plus tk with respect to arc length s with initial point 0.100. Okay, we have that initial 0.100. Okay, so what's the arc length S going to look like? Well, S of t is going to be equal to 0 to t, okay, of r prime u du, right? That's S of t. Okay, so we want to reparameterize this thing with respect to the arc length as the variable, okay, or what we're going to call S, okay, S. It's really S of t, but we're just going to call it S. Okay, so S is equal to, okay, what? Well, it's equal to the integral 0 to t of the square root of dx du squared plus dy du squared plus dz du squared. Okay, or this is r prime of u, which is r of u. So we're just going to replace all the values here up there and evaluate it at u. Take the derivative of that and evaluate at u to get this r prime of u. So again, this is going to be cosine is negative sine u squared, okay, plus cosine u squared plus 1 squared. Okay, same thing that we did before. This is 0 to t times the square root is equal to s. Okay, so s is equal to, we want to integrate this. This is going to be, again, we already know what this is. This is radical 2, evaluated from 0 to t. Okay. So we know that s, the arc length, is equal to radical 2 t, or t radical 2. Okay, so we get t radical 2 is equal to s, and we want to reparameterize this thing in terms of s, not t. So I have to solve for t. I'm going to solve for t here. Oops, solve for t. Divide by radical 2, and I get t is equal to s over radical 2. And what that allows me to do is it allows me to say, oh, well, r of s now, reparametrizing this, r of s, is equal to the cosine of s over radical 2 plus the sine, or we'll say this is I, okay, plus the sine of s over radical 2j plus s over radical 2k. Okay, and that's reparametrized in terms of the arc length, not the parameter t, okay, of the original function. This is the, okay, or the space curve. This is now reparameterized with respect to the arc length function. Okay, so the original function was parametrized with respect to the space curve. Okay, but now we have the space curve, okay, with respect to t, which is your position, okay, your positional vector. Now it's with respect to, okay, space curve with respect to arc length, okay, as opposed to space curve with respect to, let me think, what is t? T is going to be, what I want that to be. It's just my parameter with respect to t. I'm just going to say with respect to t. Yes. Okay. So you can reparameterize things in different parameters. Okay, a parametrization R of t, is called smooth, okay, no corners, if it is continuous and R prime of t is not equal to 0. Okay, so the derivative does not equal 0. Okay. The curvature of a curve is given as k equals dt ds, magnitude of dt ds, where t, capital T, is the unit tangent vector of R. Okay, that is that the curvature is equal to, okay, the derivative of t with respect to t, okay, all over the derivative of s with respect to t, okay, which is equal to t prime of t, okay, all over r prime of t. Okay, this is equal to, okay, the derivative of the unit tangent vector, okay, all over ds dt, which is just, okay, s prime, or the magnitude. Remember, what was s prime? S prime was the magnitude of r prime of t, right? Yeah, magnitude of r prime of t. That's what s prime was. And so we could say that this guy is equal to then the magnitude of t prime of t over r prime of t. And that's the curvature. Okay, so curvature k equals t prime of t over r prime of t. Huh. So we just took the curvature, we took the derivative of the top and the bottom, and we wrote it as a different expression here. Okay. Number 3, example 3. Okay, show that the curvature of the circle of radius A is 1 over A. Show that the curvature of the circle of radius A is 1 over A. Okay. Okay, so the equation of a circle, x squared plus y squared equals a squared. Okay, we want to know what's the curvature of this circle. Okay, how much? What's the measurement of the curvature of the circle? And they're saying that k in this case is 1 over a. We want to prove that. Okay. So let's parameterize this thing. Okay, let's parameterize this in terms of t, in terms of the parametric t. Okay, so well, how do we parameterize a circle in terms of another parameter? Well, choose sines and cosines. Okay, so x equals cosine t, y equals sine t. Okay. And then this is going to be r. So this isn't just a unit circle. This is a circle of radius a. So I'm going to let this be a cosine t and a sine t. Okay, so make that our parameter. Okay, so what's r of t then? R of t, if we think about this as a two-dimensional vector, okay, on this curve, okay, it's a plane curve. Okay, then what do we have? We want this to be, okay, a cosine t for the x coordinate I plus a sine t j. Okay, that's how we parameterize that as a space curve. It's really a curve that's in a plane. Okay, it's in the xy plane, but we're just going to use a two-dimensional vector to describe the motion of this circle. Okay, all the points, the locus of the points from the center. Okay. And I'm sorry if that's a bad drawing, but let's try to make it a little bit better. Okay, so we have the radius here. Okay, is a, and then you can have a vector. Okay, and the vector here is at a cosine t, a sine t. Okay, so that's my vector r. Okay, so a is the radius, but r is the vector. Okay, so what do we need to do? We need to find the curvature of this thing. So curvature, which we saw was t prime of t over r prime of t, right? And the magnitude of that. Okay, so we need to find the unit tangent vector, okay, and divide that by the derivative of the space curve vector. So unit tangent vector, how do we find the unit tangent vector? Well, the unit tangent vector is the tangent to this, which is r prime of t, over the magnitude, because we want it to be a unit. This is r prime of t over the magnitude of r prime of t, all over r prime of t and the magnitude of that. Oh, okay. Okay, so let's actually that's not right. I'm sorry. My apologies. Okay, t is what that is. So t is equal to r prime of t over the magnitude of r prime of t. Okay, that's what that is. And then we have to take the derivative on top of that, okay, to get t prime of t. So the first thing is let's get r prime of t. Okay, let's find out, well, what was r prime of t here? R prime of t is going to be negative a sine t I plus a cosine t j. Okay, so now we need to know, well, what's the magnitude of this thing? What's the magnitude of r prime of t? Okay, that's going to be the square root of negative a sine t squared plus a cosine t squared. Okay, so that's going to be equal to, okay, a squared sine squared t plus a squared cosine squared t Okay, now let's factor out a squared. That's sine squared t plus cosine squared t, square root. Okay, which this thing is just 1, right? That thing's just 1. So this equals the square root of a squared, which is just a. Okay, it could be plus or minus a. Actually, it can't. No, that's the other way around. No, could it be? No. I think about it for a second. Taking the square root, no, of the squared. Yeah, a could be plus or minus. However, we don't really care whether or not a is negative or positive. We're just going to take a vector that's positive. Okay. So this is the magnitude, right? Is just a. Oh, okay. So this is going to be equal to, t is going to be equal to negative a sine ti plus a cosine tj divided by a. What does that do? Well, that just eliminates the a. This is negative sine t I plus cosine tj. Oh, okay, that's cool.
Could you scroll down a little bit?
Down, like that?
Oh, thank you.
Okay, sure. Okay. How about I just zoom out? Okay, like so. Okay, does that make sense? How we got t? We all good? We're all good with how we got t? Okay. So what do we need next to get the curvature? Don't we need t prime? Yeah, we need t prime. So if t of t is equal to, big T of t is equal to negative sine ti plus cosine tj, okay, then let's find the derivative of this thing. T prime of t. Stop it. Go away. Okay. Okay, t prime of t is equal to, okay, negative cosine t I minus sine tj, right? Okay, but we want to do what? We want to get the curvature here, which is the magnitude, okay, is the magnitude of t of t over r, t prime of t over r prime of t. The magnitude of that. Okay. Well, what's the magnitude of the top here? Well, the magnitude of the top is just going to be 1, because that's the square root of negative cosine squared t, sorry, negative cosine t squared plus negative sine t squared, which is going to be the square root of 1, which is 1. So this becomes 1 over, and we already know what the magnitude of r prime of t is, that's a. Okay. And so that's the curvature. The curvature is 1 over a. Now, does this make sense? If we think about a circle, as the radius gets bigger, what happens to the circle? It's a pretty bad circle there. What happens to the circle? Well, it doesn't become less curvy, right? Really small circle is not going to be very curvy. The curvature is going to, think of it as like, I don't know what a good analogy would be. You know, it's the change in direction. Okay, so your change in direction, okay, or basically your acceleration is a lot bigger. Okay, you know, think of this as like, if you're doing this in a jet, think of that as like, you know, 11 G's, and then here, this may be 2 G's, okay? Oh, you can't see. Why can't you see what I'm drawing? Something happened there. One second. I don't know how this happened. Go away. Go away. Okay, where's my key? Escape. There we go. Is that good? Yeah, that's good. That's good. Okay. Okay. So just think of it as like acceleration. The higher you go, the wider you make your circle, the less acceleration you'll have to do. Okay. The less you're accelerating through that circle. Okay. So it is an inverse relationship. Inverse relationship. And your curvature changes inversely proportional to your radius. Okay, the curvature of a curve given by the vector r is also is also represented in 3 dimensions. It can be represented as k equals r prime of t crossed with r double prime of t magnitude over r prime of t magnitude cubed. Okay, that's for 3 dimensions. Okay, in 2 dimensions, if you have r of x equaling xi plus f of x j, this is how you would kind of parameterize just a function of x. Okay, so just think of this as f of x, right? Y equals f of x. So x equals x and y equals f of x, right? So how would you parameterize that as a vector? Well, this is how you do it. Okay. So say you just have a regular function in the x, y direction. How do you find the curvature of that? Well, the curvature of this is equal to the magnitude of f double prime of x over 1 plus f prime of x squared to the 3/2 power. So a couple of formulas there. Now, by no means do you have to memorize these, especially since it's an online class, but you just need to know how to use them. Okay. So let's do that. Let's use this information. Okay, number 4. Find the curvature of the twisted cubic Okay, r of t is equal to t squared and t cubed. Well, this is kind of interesting. What is this thing going to look like? Okay, so I'm going to go to my parametric curve grapher here. Let's see, what if I just plug in t? Oops, not capital T. T squared Where is my caret key? I'm just going to use my keyboard. Okay. Squared. Okay, and t cubed. Cubed. Okay. Oops, not t3. Okay, t cubed. Okay, and then I'm going to redraw this thing. Okay, and so it might be kind of hard to see. Okay, but it kind of comes out and it just goes up forever. Okay, it's not really a helix because it doesn't spin around. It just kind of like goes out in kind of a spiral, goes out forever. But it starts getting really high really fast, which makes sense because the z component is cubed the x component. So it starts out real small, but then it starts gaining height and depth, okay, really fast. Okay, the x coordinate stays relatively small. The y coordinate and the z coordinate start gaining speed, and so this is called the twisted cubic. Okay, it's twisted. That's kind of a good perspective there. Kind of like a big slide that goes off to infinity. Okay, anyway, I just felt you had to see, you should see that at least once, what that thing looks like. Okay. Okay, and we want to find the curvature at 0, 0, 0. Okay, what's the curvature? What's the initial curvature of this thing looking like at 0, 0, 0? Okay, it looks like it's probably pretty curvy. Pretty curvy as the thing goes up, and then it just goes on up forever. Whoosh. Kind of goes like that. There's a big whoosh. Okay, make sure you do the whoosh when you draw that. Okay, so we want to find the curvature with respect to the formula that we just had. The curvature, okay, is equal to r prime of t crossed with r double prime of t all over r prime of t cubed, right? That was our thing there. Okay. So what's going to be r prime of t? R prime of t is going to be equal to 1, comma, 2t, comma, 3t squared. Okay. What's r double prime of t? Well, that's 0, comma, 2, comma, 6t. Okay. So now what do I have to do? Well, I have to cross product these. Okay, I have to cross product these. Oh, this is magnitude. Sorry. Yeah. So let's cross product these guys. So we're going to go ijk. Okay, we want to cross product r prime and t. So we're going to put the r prime and t first. Okay, so that's 1, 2t, 3t squared. Okay, the r double prime goes 0, 2, and 6t. Okay. Let's find the determinant of this thing. Okay, so I'm going to cross off this row I, the first column in the first row, we're going to cross that off. We get t, 3t squared, 2 and 6t, I. This is minus, okay. This is going to be 1, 3t squared, 0 and 6tj, plus, okay, 1t, 0 and 2k. Okay. So this is equal to.
Professor, isn't it supposed to be 2t and not t under j?
Oh yeah, thank you. Thank you. Good. This is 2t. Thank you. Okay. So yeah, 12t squared minus 6t squared I. Okay. Minus, this is going to be 6t because everything else is going to go to 0. 6tj plus, this is just 2k because the other thing goes to 0 as well. So this is going to be equal to 6t squared I minus 6tj plus 2k. Okay, so that's the cross product. Okay, so we want to find the magnitude of this thing. So k is equal to the magnitude of 6t squared I minus 6tj plus 2k over the magnitude of r prime. Well, what was r prime? R prime is, we could put it as I plus 2tj plus 3t squared k. I want the magnitude of that thing cubed. Okay. So let's see what we get here. Okay. So magnitude of the top is going to be the square root of 6t squared plus negative 6t squared plus 2 squared. Okay. All over the bottom, which is going to be the square root of 1 squared plus 2t squared plus 3t squared. Okay, and all of that cubed. Okay, so the thing here is going to be what, 36t to the fourth plus 36t squared plus 4. Okay. Okay, square root that. Okay, all over 1 plus 4t squared plus 9t to the fourth. Okay, and all of that. Okay, yeah, all of that is going to be, think about this for a second, square rooted to the third power. Okay, So I could factor out a 4 here if I really wanted to. 2 times the square root of 9t to the 4th plus 9t squared plus 1 all over the square root of 9t to the 4th plus 4t squared plus 1. Okay, all to the 3rd power. Okay, and that's about as far as I can go with that, because they're not identical. And however, this is k of t, right? This is a curvature at time t, or at position t. And where did we want to find and for what value of t are we looking for? Well, we're looking for the curvature at time 0, right? When t is equal to 0, when the parameter is equal to 0. Why? Because the original function, the original vector was t squared, and t cubed. And we wanted to know, well, what happens at 0, 0, 0? What's the curvature at 0, 0, 0? Well, that means that all these t's would have had to be zeros. So basically we're asking at t equals 0, what is the curvature? So we're going to plug in 0, and we're going to say, this becomes t times radical 1, which is just 1, 2 times radical 1, which is 1, all over radical 1 cubed, which is just 1. So the curvature ends up being 2. Let me plug this in so that you know what I did in your notes. 9 times 0 to the 4th plus 9 times 0 squared plus 1 all over 9 times 0 to the 4th plus 4. That's a 4. That's a 9. 4 times 0 squared plus 1. Okay, and that equals 2. So the curvature there was 2. Okay, let's do a real quick one in 2 dimensions. Okay, let's look at the function f of x equals x squared, and let's get the curvature of the parabola at 0, 0. What's the curvature of the parabola at 0, 0? Well, in 2 dimensions, the curvature is f double prime of x over 1 plus f prime of x squared, okay, to the 3 halves. It's really the arc length. It's the arc divided by the arc length cubed. Okay, if you were to integrate that. Okay, but we're good here. Okay, so what's f prime of x? F prime of x is equal to 2x. What's f double prime of x? Well, it's equal to 2. So this is going to be the magnitude of 2 over 1 plus 2x squared to the 3 halves power. But once again, we're evaluating when x is equal to 0. We want to know at 0, 0, right? So we can plug into 0 here, and we get 2 again. K of 0 is equal to 2. So the curvature of that is also 2. Okay, so this is K of x equals that. Okay, let's end this with a couple of definitions. Okay, the unit normal vector. Okay, the unit normal vector called capital N of t is equal to the unit tangent vector. Take the derivative of that, and then it's basically the derivative of the tangent vector. It's the unit derivative of the tangent vector of the unit. No, how do I want to say this? It's the unit vector of the unit tangent vector. So this is the unit vector of the derivative of the unit tangent vector. That's how you want to say it. Okay, we're taking a unit vector of the derivative of the tangent vector. And that's called the unit normal vector. Okay. So let's look at our circle here real quick. Okay, we said that our original vector is r of t, and then our tangent vector is orthogonal to this on a circle, right? Okay, so our tangent vector is t of t. We'll make that a unit. We'll make that a unit tangent vector. And then, yeah, what's going to be the normal vector? Well, think about the right-hand rule here. Okay. If I take this guy into this, then won't it be coming out? Right? So this is r of t. Think of this as r of t. Okay, r of t, this is t of t. And then that's orthogonal to both of them. N of t is orthogonal to both r of t and t of t. So think of it like the corner of a wall, right? So you've got this wall here, and you've got the corner of the wall, right, coming in. And so that's that all three of these are orthogonal to each other. So you could say that this is, okay, r of t. This is t of t. That's this guy here. And then this is n of t. Okay. It's orthogonal to both r of t and t of t. Okay. So that's for a circle. Now it's not always going to be that clear cut, but the n of t will always be normal to the other two. Okay, even if it's not, okay, even if it's not a nice, okay, a nice r or t, it's still going to be orthogonal. N, okay, will always be orthogonal to the other two. Okay, so yeah, that's the unit tangent vector, and this is orthogonal to t of t. Orthogonal to the unit tangent vector to t of t. It's orthogonal to the unit tangent. It's called the normal unit normal vector. It's always orthogonal to the unit tangent vector. Okay. Okay. So okay, we'll get into the analogy of this in a second. Okay, but think of this as r of t as my position, r prime of t as my velocity, and r double prime of t as my acceleration, right? Okay, well, what's t? Well, that's just a unit tangent vector. That's just the velocity, right? We're just making it one unit. Okay, and then what would n of t be? Well, n of t, wouldn't that be kind of like your second derivative? You're taking the derivative of a derivative, right? We're just making it the tangent vector. We're making it one unit, and then we're taking the derivative of that tangent vector, unit tangent vector. Okay, this is one unit. This is one unit. Okay, and we could okay, we could make this one unit if we really wanted to make it a unit vector. We'd call it u of t. Okay, and that's a unit vector. Okay, so we could make each of these kind of, and these aren't the same, not the same. Okay, but but the analogy is similar. Okay, they're both a unit of acceleration. So just keep that in mind. But they're not equal. Okay, the binormal vector okay, b of t is equal to t of t crossed with n of t, okay, which is orthogonal to both t of t and n of t. It's kind of interesting. Okay, and because both t of t and n of t are unit vectors, it itself is a unit vector. When you cross two unit vectors, you get another unit vector. Okay, and is itself also a unit vector. Okay. Okay, let's jump into 13.4, which is motion in space. Motion in space. You gotta say that kind of spacey. So water checkpoint. I've been watching too much WODZ. So it's like water checkpoint. It's the time in the class. You go to your fridge, grab yourself a water, and we drink up. All right. Water checkpoint. Okay. Position is R of t. Velocity, I just covered this, okay, is R prime of t, which equals the V of t. Okay, V of t. Okay. If you want to make that a unit, one unit in velocity, you'd have to unitize that, make that a unit vector, and then it'd be t of t. Speed, which is velocity without a direction, and it's a magnitude. The speed is the magnitude of the velocity vector. So how do you think we're going to get speed?
Double prime?
Say that again?
Double prime?
No, no.
Magnitude of the velocity vector.
I couldn't hear you. Sorry. Say that again. Can you not understand me?
Magnitude of the velocity vector.
Okay. So it's the magnitude of the velocity, right? So how about the magnitude of R prime of t? Make sense? Okay. Or the magnitude of the velocity vector? Either one. Okay. Which is what I've seen this before. Anybody remember what that was? We've seen that before. The magnitude of R prime of t. Where have I seen that before? Oh yeah, that's ds dt. That's the derivative of the arc length with respect to t. Look at that, making connections. Okay. What about acceleration? Acceleration, okay, is r double prime of t, or v prime of t, which we're going to call a of t, okay, for acceleration. Oh, makes sense. Okay, number one. The position vector of an object moving in a plane is given by r of t equals t cubed I plus t squared j. Okay, find velocity, speed, and acceleration when t is equal to 1. Okay, time 1. Okay, so v of t is just going to be the derivative of this thing, right? So that's going to be 3t squared I plus 2tj. Okay, so that's the velocity. Okay, the speed, okay, the speed, okay, is the magnitude of the velocity, which is going to equal the square root of 3t squared squared, okay, plus 2t squared, which is going to equal 9t to the fourth plus 4t squared. So that's the speed. Acceleration. Okay, acceleration is going to be a of t, which is going to be the second derivative. So that's 6ti plus 2j. Notice that the y component doesn't have anything to do with the time component. That's kind of interesting. So it means that it's a constant acceleration in the y direction. Interesting. Okay, so let's evaluate this at 1. Okay, so what's v of 1? Well, v of 1 is going to be equal to 3i plus 2j, which you can think of as 3, 2 as a vector. Okay, what's the speed going to be? This is going to be the square root of 9 times 1 to the fourth plus 4 times 1 squared, which is the square root of 13. Okay, so that's the speed. Okay, what about the acceleration? Okay, the acceleration evaluated 1 is just 6i plus 2j, which is equal to 6, 2, which is kind of interesting. So yeah, this is pretty interesting. So yeah, this is in 2 dimensions. So let's see what happens if we graph this thing. It might be interesting to see what this looks like if we graph it. So let's go to our parametric 3-curve 3D grapher. Okay, I'm just going to let z equal 0 in this case. There is no z. Okay. Zero. This guy is going to be, y is going to be t squared, and x is t cubed, right? T squared. So t squared. Okay. Tab. Oops. Tab back. Okay, and then this is t cubed. Okay, let me redraw this real quick. Redraw display. Okay, where's x and y? Okay, let me use the mouse. Okay, so it's looking like it's going off. Okay. X and y. Should just be following that XY trajectory. Yeah, it is. Okay, so it's just whoosh. It's whoosh. Here's X and here's Y. What if I did the traditional XY? Positive X's, positive Y's. Let's go here. There we go. Traditional XY looks like this. Okay, X is t cubed, Y is, that's good. Okay, traditional XY axis. Okay, and then the position vector is r of t. Let's look at the velocity vector. So they give me the velocity vector too. Wish I could move this over, but I can't. That sucks. Okay. And so, I don't think they give me the acceleration function, but I can put it in because the acceleration function is just 6t. Well, it's all good. I don't want to mess with that. Okay, but it kind of gives you an idea. There's the position and there's a little velocity. Okay, but notice that at 1, the velocity is at 2 and the position is at 2 for the y value. That's kind of interesting. Okay, number 2. Okay. Okay, R naught. Okay, R naught is equal to 1, 0, 0. Okay, so we're starting off at 1, 0, 0. Okay, V naught is equal to I minus J plus K. Okay, this has initial velocity. Okay, so R naught has initial velocity. Let me write this as just I. Okay, R naught equals I. Okay, has initial velocity here, and acceleration. Its acceleration is a of t equaling 4ti plus 6tj plus k. Okay, find its velocity and position at time t. Find its velocity function or vector function and its position vector valued function. Okay, so basically what they're doing is they're giving you initial conditions so that you can work backwards. Okay, so notice that basically we have r of t, r prime of t, and r double prime of t. And they're saying r double prime of t is equal to 4ti plus 6tj plus k, right? And they're saying, we want to work backwards, so how do we find the antiderivative? Well, we integrate, right? So we're going to take this a of t, and we're going to integrate, okay, for t, okay? So on t. So we're going to say, v of t is going to be equal to the integral of a of t dt. Does that make sense? So v of t is going to be equal to okay, the integral of 4ti plus 6tj plus k. Okay, so let's integrate this component by component dt. Okay, so this is going to be 2t squared I plus 3t squared j plus tk plus c, some sort of c, right? So that's going to be, okay, but here's the big but. Okay, v naught is equal to what? Well, do you see how each of these here have a t component to them? If I plug in 0, what happens? Well, it all goes away, right? And that will leave me with c. And so I know the constant, okay, the integration constant was equal to I minus j plus k. I minus j plus k. That's what I was given as v naught. So I know that this is going to be 2t squared plus 1i, okay, plus 3t squared minus 1j plus 1k, right? So that's going to be 1 plus 1. Sorry, this is t plus 1, okay, plus t plus 1, k. Okay, so this is v of t. So now how am I going to get my position vector? R of t. Well, isn't R of t going to be the integral of v of t? And so and then they give us our initial position, right? They give us an initial position of just 1, 0, 0. Okay, so let's integrate again. Okay, so this is going to be what? 2/3 t cubed plus t I plus what's this going to be? T cubed minus t j plus t squared over 2 plus t k plus c. Okay, so that's r of t. But once again, we know that, okay, r naught, okay, or when t is equal to 0, we just get I, which means that it's the vector 1, 0, 0, right? Okay, so we know that everything goes to 0 here. This goes to 0, this goes to 0, that goes to 0, except for one stinking I. So that means that it's 2/3 t cubed plus t plus 1 I plus t cubed minus 3 or minus t j plus t squared over 2 plus t k is r of t, using those initial conditions. Okay, let's do some physics. Fun with physics. Okay, next two problems are physics problems. Okay, number 4. An object with a circular path and constant angular speed omega, okay, or w if you want it to be w, again, has position r of t equals b cosine omega t I plus b sine omega tj. Okay, so this circular path has constant angular speed omega, has this position. Okay. Okay, find the force. Find the force that is directed toward the origin. Okay, so the force that is directed toward the origin. Okay, so we have this circular path, right? Okay, and so it's out here, B. Okay, B is our radius. Okay, and then we have, okay, and then we have our velocity, which is orthogonal to that, and then our acceleration, which is orthogonal to that. So our acceleration is actually pointing inward, right? So our acceleration is actually pointing inward. Okay, A, right? This is V. Okay, so position. Okay, A is pointing inward. Okay, and so what's the force? Well, the force is going to be mass times acceleration, right? So force equals ma, according to Newton's second law. Okay, so force equals ma. Therefore, we're just going to have mass times acceleration. Okay, so what we want is we want to find out what is f of t equals m times a of t. Okay, what's the acceleration at time t? Okay, what's the acceleration at time t for this thing? Okay, so let's see what happens, and we're going to see that it's opposite. We're going to see that it's opposite r of t. We're going to see that okay, that it's going to be opposite r of t. So let's find a of t. Okay, so we know that r of t is equal to b times the cosine of omega t I plus b times the sine of omega t j. Let's get r prime of t here, which is our velocity. That's going to be using the chain rule, right? This is going to be negative b omega sine omega t, I, right? Because we have to take the derivative of the outside and the inside. Okay, plus, this is going to be plus b omega cosine omega t j. Okay, now let's do our second derivative, which is our acceleration. So we're just going to do the same thing over again. Basically, this is negative b omega squared cosine omega t, I. This is going to be minus b omega squared sine omega tj. Okay. So the force is equal to the mass times negative b omega squared cosine omega t I minus b omega squared sine omega t j. Okay. What I'm going to do is I'm going to factor out the negative and the omega squared. Okay, so force is equal to mass times, or negative mass times omega squared times b cosine omega t I plus b sine omega t j. Well, what was this thing? Wasn't that just my position vector? Isn't this just r of t? Yeah, it's just r of t. So force equals negative m omega squared RT. So it's negative direction, right? It's the opposite direction of the original position vector, which is the centripetal force that is being pulled in on the object. Okay, so again, that's centripetal force, which is opposite the position vector. Okay. Okay, let's look at projectile motion. Okay. Okay, so the parametric equations for the trajectory are, okay, x equals v naught cosine alpha t, and y equals v naught sine alpha t minus 1/2 g t squared. So we take into account, okay, initial velocity and acceleration of gravity due to time. Okay, so that's for trajectory, right? So that's when we, okay, when we are here and we, okay, so this is our path, right? So it's should be a parabolic path if we're up here. Okay. Right. Okay, so we're going to release it with some initial velocity, okay, at some sort of angle, okay, alpha. Okay, so this will be v naught at angle alpha. Okay, and then it'll fly through the air and crash land at some other point. Okay, so number 5. A projectile is fired at a speed of 150 meters per second at an angle of 45 degrees from a position ten meters off the ground. Where does the projectile hit? And with what speed? Okay, so let's put in our parametric equations here for what we know. Okay, where x is equal to, okay, v naught cosine alpha t, and y is equal to v naught sine alpha t minus 1/2 gt squared. Okay, so v naught is going to be 150. So x is equal to 150 times the cosine of 45 degrees t, and y equals 150 times the sine of 45 degrees t minus 1/2 gt squared, which g we're doing in meters, so that's 9.8 meters per second. Okay, times t squared. Okay. So this is going to be 75 radical 2 t, x is equal to 75 radical 2 t, y is equal to 75 radical 2 t minus 4.9 t squared. Okay. However, we are 10 meters off the ground, which means that we have to add 10 here. Okay. Plus 10. Okay. So I guess we could have put in here plus some sort of h naught. Okay, plus h naught, which is fine. Okay. Okay, where does the projectile hit the ground, right? And with what speed? Okay, so we know that we have a parabolic arc, right? And that the height of the parabolic arc there, okay, is the vertex, right? Okay, so if I let x equal, or let y equal 0, then that should give me this point and this point in terms of t. Does that make sense? Okay. So it doesn't matter that I start here, okay? It just means that I'm going to get a negative result for t on one side and a positive result for t on the other side. Okay, so let's figure out what happens when the height equals 0. So set this equal to 0, and let's solve. Okay, well, you can just plug that into the quadratic formula. Okay, and after you do that, you get y to be approximately 21.74 seconds. That's the positive value. Okay, 21.74 seconds. Okay, so how would I find out the distance that this went, right? Or the x value. Okay, the height is 0, but what's the distance? Well, the distance, okay, that this goes is going to be that x value, which is going to be x equals 75 radical 2 times t, which is 21.74, which comes out to be approximately 2,306 meters away. Okay, what's the speed here? The speed is the absolute value of the velocity vector. Okay, v of t. Well, we need to find the velocity vector. We know that r of t is equal to 75 radical 2 t I, okay, in the x direction, okay, plus 75 radical 2 t minus 4.9 t squared plus 10 in the j direction. Okay, so that's r of t. So I'm sorry if my r's and my v's look similar. The speed is v and this is r. Okay, so that was r of t. So what's the derivative here? What's r prime of t? Well, the derivative is going to be 75 radical 2 I plus, this is going to be 75 radical 2 minus 9.8 t j. Okay, so that equals v of t. Okay. And so we want the speed when this thing hits the ground, right? We want the speed. So let's work on the speed first. Okay, so this is 75 radical 2. We want the okay, the magnitude of this. 75 radical 2 squared plus 75 radical 2 minus 9.8 t squared, and then take the square root of that. Okay, so, but I'm going to replace that t once again with the t that I had discovered was the time that it took to hit the ground. So this is the square root of 75 radical 2 squared. Okay, plus, which comes out to be 11250, plus this thing, which is 75 radical 2 minus 9.8 times 21.74. Okay, all of that squared. Okay, which comes out to be 11250 plus approximately 11446, okay, which is equal to the square root of 22696, which is approximately 150.65 meters per second. Okay. What number was that? 4? 5? Did we skip a number? No, 4. Oh, we didn't. 4, 5. Let's go to 6. Okay. Okay, let's look at tangential and normal components of acceleration. So tangential and normal components of acceleration. Okay. Tangential and normal components of acceleration. Okay, so AT, okay, what is AT? Well, let's look at a curve here, okay? And at this curve, okay, I'm gonna have an acceleration. Call this A. And what is the tangential acceleration? Well, it's tangent to the curve at A. This is A tangential. And then what's orthogonal to the tangential is the normal. This is A tangential. It's not orthogonal to the original acceleration, but it's orthogonal to the tangential. These two are orthogonal. And that's A normal. Okay? That's the normal acceleration. It's just that orthogonal acceleration, it's the acceleration component that is orthogonal to the tangential component. Okay. So the tangential component is r prime of t dotted with r double prime of t all over the magnitude of r prime of t. Okay. The normal component, very similar, is the magnitude of r prime of t crossed with r double prime of t all over the magnitude of r prime of t. Okay, number 6. A particle moves with position r of t equals t squared comma t cubed comma t squared. This is t squared, sorry. T squared comma t cubed. Okay, find the tangential and normal components of acceleration. Find a of t and a of m. Okay. So what do we need? We need the first and second derivatives here, right? So what's r prime of t? 2t, and 3t squared. What's r double prime of t? Well, that's 2, and 6t. Okay, so let's look at the tangential first, I guess. Okay. I mean, we're eventually going to need the magnitude of this thing, so maybe I'll just calculate it now. Get it out of the way. Okay, what's the magnitude of r prime of t? This is going to be 2t squared plus 2t squared plus 3t squared, right? Okay, this is going to be 4t squared plus 4t squared. That's 8t squared plus 9t to the fourth square root. Okay, so come back to that a little bit later. Okay, so what's the tangential part of this? Well, that's AT is equal to r prime of t dotted with r double prime of t all over, okay, r prime of t magnitude. Okay, so let's dot this r prime with r double prime. Let's do the dot product real quick. Well, that's just going to be 2t plus t, which is 4t, plus 2t plus t, which is 4t, plus t cubed plus times 3 3t squared times 6t, which is 18t cubed. Okay, all over the square root of 8t squared plus 9t to the fourth. Okay, so this is going to be equal to 8t plus 18t cubed all over. Now I could factor out a t on the top and bottom here. Let me do this step first. I'm going to go a t out there, and then I'm going to get this to be 8 plus 9t squared, right? So I just factored out a t, pulled it out in front. Okay. And what is that going to do? That's going to cancel with one of these t's. So this becomes squared. So this is going to be equal to 8 plus 18t squared all over the square root of 8 plus 9t squared. And that's as far as I can go with that one. Okay, what about the other one here? Okay, so a sub n is equal to the cross product. So we're going to have to do the cross product. Okay, so a sub n is equal to r prime t cross r double prime t magnitude over the magnitude of r prime of t. Okay, so let's do the cross product. So I, j, k. Okay, what was r prime of t? That was 2t, 2t, and 3t squared. 2t, 2t, and 3t squared. What was r double prime? That was 2, 2, and 6t. Okay, so let's figure out what this is going to be. This is going to be 4t minus 4t. I'm sorry, no. This is going to be 12t squared minus 6t squared, which is just t squared, 6t squared. Okay, so that's 6t squared I minus, this is going to be 12t squared minus 6t squared, which is just, again, 6t squared. So that's 6t squared j. And then k is going to be 4t minus 4t, which is 0. So that's plus 0k. Okay, so that's that guy. Now I want to find the magnitude of this thing. So that's the square root of 6t squared squared plus negative 6t squared squared. Okay, so this is really going to be 6t radical 2. Is that right? 6t. No, I did that. Did I do that? Oh, I left off the squared here. That's why. 6t squared squared. So this is 6t squared. There we go. Okay, so you can just pull that 6t squared out in front because they're being squared. And then you've got two of them, right? You've got two of them. I mean, if you really want to multiply this all out, you can. You know, you're going to get square root of 72 t to the fourth. Okay, and then you can pull a 36 t squared out of that. Yeah. Okay, a 36, square root of 36 is 6. Okay, so that equals that on the top. Okay, and then we get on the bottom, we get this t times 8 plus 9 t squared. The t's cancel, and I'm just left with 6t radical 2 over the square root of 8 plus 9t squared. And that's the a sub n. Okay. Okay, I'm gonna stop there for today. Okay. Does anybody plan on coming to office hours? Let me know, otherwise I'll just cancel it. See you guys on Monday. Make sure you do your review.
Bye. Thank you.
Welcome.